have quite a bit of stuff to go over. Today, over the next couple of hours, we're going to do both an intro to what an MEng program is here at Berkeley, EECS, and also you'll be able to see faculty pitch the Capstone projects. We have already a bunch of projects that were kind of listed on the web, but some more are coming in, so we're going to have an opportunity for faculty to kind of present to you what they would like to work with you on during the next year, so that you're more informed to to list your priorities, and I'll explain everything kind of in the what our procedure is for matching and everything else. But yeah, and then in the end of the hour 2:30 to 3, we'll have a student-faculty mixer, so people who are available can stay and just chat about capstones or MEng at Berkeley in general. However, if you have any questions during the presentation for any project, please ask. Even in the overview section, we're happy to answer. Don't wait till the end of the thing to raise a hand, okay? So let's get going. My name is Vladimir Stojanovic, and I'm a vice chair for master's programs in the EECS department. MEng is one of them, fifth-year masters, and Mass IC is another one. Of course, people who do all the work here are Michael, Son, and Shirley, and I really want to acknowledge their contributions for working on getting you folks admitted and also organizing this whole event. So once you decide to come to Berkeley, come on campus, Michael and Shirley are going to be primarily your contacts with the department regarding course selection, any possible imaginable thing that you have about the program, and then of course I'll be here also to help out together with them. Just a brief overview, and I'm sure you've already looked at this hard when you decided to apply to Berkeley. Our MEng program is kind of specific with respect to maybe other master's programs that you've seen in that it emphasizes both three components. One is the breadth of information. So being able to understand, not only have technical breadth, but be able to have soft skills, management skills, being able to form a team, understand how to work within a team, and understand how to write and present, are things that may sound redundant today, but believe me, if you look at any technical company, 5 years into your job, pretty much every technical company has a very shallow technical ladder. You will work for a while, and then in the end of the day, you will become a project lead and a manager. And all you have to do all day long will be these soft skills. And so learning them early on to help you be a leader and an effective member of a team is something that we put a lot of emphasis on. So you'll see these core leadership curriculum courses. And it's one thing if you go through them thinking, oh, these are just some requirements I have to fulfill. That's one experience. Another experience is really going through them and realizing that these are the tools, these are the instruments that you will use later, actually very soon in your career, to be able to advance and become an effective team lead and a manager after that. So keep that in mind. You'll get more out of them that way. Right? The second one that is very special to this program is the Capstone project. You'll find other master's programs throughout the country and the world that emphasizing courses. You come in, do a bunch of courses, you're out, you're specialized, and that's it. We at Berkeley pay special attention to hands-on education. And the reason is that that's the best way to learn. One thing is to do a class and even a project within the class. But if you have a year-long project with a faculty member and a team where you're really diving much deeper than in anything you've done in the class, there's a different level of understanding and knowledge that you can gain. And that's what we organize, capstone projects. It's not easy to run capstones. Those are actual projects that people work on. So this is, again, another thing that what we've seen in the past, it varies what students get out of it. And simply because they don't realize the value of it early on. They come in here, get swamped with a bunch of classes, job search, all those things, and they don't realize that diving deep into the capstone is probably the most valuable experience you're going to get here at Berkeley. Because even if you go do a job interview, first thing people are going to ask you, what big project have you worked on? Right? described to me in depth. And Capstone is the thing that you should be talking about, right? So pay attention to that, how it's set up, what are the big ideas in that capstone, and then try to be an active contributor. That also gets you a really good potential letter and a recommendation from the capstone faculty member into their network. It's a very beneficial experience. So we'll talk a lot more about that. And then we have, of course, courses, and courses are both in the technical depth and breadth. So we have a core, which is your emphasis area where you apply to, and then the breadth requirement. So, you know, in summary, kind of in terms of graduation requirements, you have 4 courses, so 2 per semester. These are technicals. And 3 are from the list in your core area. So you've applied to a certain area. That's where you're going to be matched with a capstone project as well. And then we're going to let you pick the courses, and we'll explain a little bit what the logistics is when these things happen. These courses have to be at a 200 level. Usually, our courses are organized so that the introductory course is in the fall term, usually with a suffix of A, and then there are courses in the spring term that are basically a more advanced course on the same topic. So you get kind of a sequence that gets you the depth. You can also pick technical course outside of your emphasis area, and that's a breadth. So you really should be also looking for that to pick up the extra tools, because you never know where life is going to take you. The more narrow you get, sometimes is good, but also having the background to move and shift disciplines is also pretty good. So try to balance all that. Of course, GPA is another graduation requirement, so GPA above 3.0 will get you graduated, as well as what we have right now is there is a capstone kind of a project report, but the graduation requirement is actually an oral exam, which is essentially a presentation in May in which your capstone faculty member and a member of the MH committee, sometimes that's me, sit down and listen to your oral presentation and ask you questions about your capstone. What have you done? So the whole team presents, and that's basically your graduation requirement as well. Okay, diving into the capstones, we have right now 2 flavors. One flavor is what we call capstone design experience. That is essentially a project that is also tied with a course sequence. Because in a lot of cases, and here I'll show you, we have one example of that in the list today. In order to start being effective on a capstone, you kind of have to learn something first. And so it doesn't make a lot of sense to start hard on the project when you're kind of learning the ropes and the tools at the same time. And so here we kind of spread it so that you have an intro class in the fall, plus a little bit of capstone exploration, just understanding the topic. There's some connection with Funk, understanding kind of how that idea projects to market, really understanding the context for the project, but not really diving very deep. That gives you time to catch up on the background tools. And then in the spring term, you go hard on the capstone because you've learned tools that are required to be able to do something. So that's what we call a capstone design experience. The capstone project, and you'll see a whole bunch of those today as well, is such that you start pretty hard on it in the fall term, and then you ramp up in the spring term. Sometimes you will also find a background class, and we try to pair you up with those and suggest those during the summer. That will also get you going faster in the fall term with the capstone project, right? So those are kind of the 2 flavors that we have. Now, a lot of people last year petitioned for us, probably about more than 30 admits actually petitioned for us to consider a 3rd semester option. And the reason for that is that historically, you come to Berkeley, there are really interesting classes, really interesting capstones, but a lot of people just feel overwhelmed that in 9 months they have to do all of these things, and they would like to stay a semester longer, dive deeper into some topics, like let's say a capstone, but also be able to take an extra class and also have the benefit of a really good summer internship, right? And so we basically listened to that and created this pilot option. The reason why I'm saying a pilot, it was not on your checklist when you were applying that this is an option, right? But the pilot is structured in a way that you start regular 9 months, 2-semester program, and then you essentially take the first set of courses that are in the fall. Then after the fall term, you decide whether you want to apply for this program or not. Based on your performance in the fall term, as well as classes, as well as the opinion of your capstone faculty, you get admitted or not into this program. And if you look at here, kind of the third semester, it's really bulk of the work is individual study with a faculty advisor, right? So a lot more in-depth on the capstone project, because by that time you figured out kind of what are the most and I've seen this like throughout in capstone presentations, people really by sometime May timeframe dive into the work a lot, and you see that they really, really would like to spend a few more months really kind of completing that topic and becoming experts in that area, right? And that's what we're trying to achieve here. So it'll be a lot more in-depth with the capstone faculty. There's another opportunity to lead the follow-on capstone team. Essentially, that fall, a new cohort is starting, and you're already an experienced person, so you get that leadership experience as well in agreement with the capstone faculty. And you have one more technical course in your core to take, plus one more elective that you choose, or you don't have to do it, you can balance it with a capstone. Now, so that's essentially the structure. You will basically make that decision both on the technical and of course on the financial side, because this extra semester costs extra money, right? And so you can apply, and then during the spring term, basically by I think April timeframe, we require a commitment or something, right? Yeah, by April. So you'll have some time between when you apply and see how your job search goes and what you want to kind of finalize your plans. But this is one option that we're opening up to people right now. This year, I think we had about 20 applications, and we granted about 13, I think, ish, right? Yeah, and then of these 13, we have about 8, 9 people who decided to stay, right? So just to give you kind of a ballpark number. Okay, in terms of the project logistics for capstones, EECS faculty are the advisors on all the capstone projects. You will also very often be paired up with a graduate student who's going to be essentially a tutor, in a sense, to help you with tools, setting up the tools, small hackathons to get things going, and then you will also interact with the faculty member, essentially on average once a week, kind of have like a research meeting and sit down and see what's going on. But more frequent interactions will be also with grad students who will help you kind of get into the gear and do a lower level debug, basically, that faculty often don't have the time to do. The logistics is the following. We're recording this presentation and the slides. So when you go back home, we will blast this to all the admitted students. And so you will have this slide deck as well as the videos to kind of refresh on what's being offered. And we're going to update the website with capstone abstracts and descriptions. So you'll have some material between now and sometime in June to try to figure out what interests you. Also, there's a list of faculty emails in this presentation that feel free to contact any one of them about any of the projects between now and June timeframe. If you want to learn more, you're on the fence of prioritizing one project versus another, you're now admitted students, should feel free to contact the faculty and discuss more with them about what you're interested in. In fact, I strongly encourage that. It gets you closer to the faculty who've proposed these capstones. They want to work with you. They want to get to know you, okay? In June, we'll be sending a survey that says, okay, here's a list of capstones, name your priorities, first, second, third. And Then we were going to try to run a match. We have some constraints on our side because we want to form teams of 3 to 5 people. These are projects that cannot be done by a single person, and we need to form the teams. Teams also help you with the leadership and fun component because a big chunk of this experience is learning how to work in a team. Some of you have come from schools where projects that you do in courses are individual projects. You don't have much experience working in teams. This is a very critical component because guess what? You go in a company, you're not going to be working alone. You're going to be working in teams and small groups, again, 3 to 5 people initially and then bigger organizations. So you need to learn how to work in teams, get together well, plan. You will have joint exercises in team planning, who does what by what date, handling sometimes conflicts. What if someone in your team doesn't do some ABC until that date? That's all part of life. Courses are hard, there's a midterm, someone skipped a deliverable. You need to organize within the team how to handle it. We will help you, and especially the Capstone advisor, and also on the Fung side, Alex is basically involved in running the leadership component. He will also try to mitigate these things, but ultimately it's your learning experience to figure out how to make the team work throughout the year, right? And it's something you should be proud of once the thing ends, that you've been able to get the team to work together, right? Not just yourself. So because of these constraints, we may sometimes place you in your second choice. Okay, third, I don't know if we ever have done, but really it's going to be first or second choice. Okay, if you're not happy with that initial placement, you should let us know. We will probably by end of June, early July already let you know what your initial placement is. You should immediately let us know if you're not happy with your assignment, so that we have some time to try to rejiggle the algorithm to try to make sure that you are happy, okay? The reason for that is also that immediately after that placement, Michael is going to start sending you another survey, which is your course preference survey. Because now that we know which capstone you're in, we know how to prioritize the courses that will help you be successful in that capstone, right? Because each capstone has a certain background that is required to be able to be successful in it. And so again, you also will be able, by selecting a capstone, to know more which background courses you want. And again, that will help you fill out that course preference survey. So by the time you come here in August, everything is settled. You've chosen the courses, you know which capstone you're in, and you're good to go. There's many, many things to do, very quick ramp up. You don't have the time at that point to change things, right? So that's why we urge you, if you want to change something, please interact with us during the summer so that we can fix all that before you come in, right? Because when you come in, you'll be drinking water from a fire hose. And so there's a lot of balls in the air. It will be very difficult to change things. Of course, if you come in and something detrimental's happening, that something really out of the ordinary, the team's falling apart for whatever reason, of course we're gonna help you change things and be happy, right? This is not like a stone wall, but please keep in mind that we're one of the rare departments that does this procedure simply because our program is hard and we want to get you going and effective from day one when you come to Berkeley in August, right? So we don't have the time for shopping, going around, etc., because really the program starts day one, right? And in fact, if you know where you're placed and what courses you're taking, you can take some portion of the summer to kind of get some context for it, etc., if you're interested. Okay, those are kind of the capstone logistics. Here's a list of kind of on 2 pages of the capstone projects, the area, and also the contact faculty member. You'll notice that some projects cover multiple areas, and those are the ones that we particularly like because they really show you that a lot of projects are multidisciplinary. And regardless in which area you are admitted, if the project has these multiple areas, if you see one of the ones that you are in, you should feel free to put that one on your preference list, right? And you'll be considered for that project, right? Because that project has a need for students from all of these areas, okay? Again, that's a list. And now I want to kind of kick the gears and kind of show you some of the content. Some of the faculty couldn't make it, but they made really cool videos, so I'm going to play those, and others are going to be here. So Alex Byrne has some very cool projects, so I'll play you his video.
All of you have probably read or seen on TV futuristic, Star Wars-looking style rendering of what the future might look like. One problem I'd like to talk about today is how we use self-driving car to make traffic better and specifically reduce traffic jams. In 2008, an experiment was conducted in Japan in which people were asked to drive at 25 miles an hour in a circle. A simple task, you would think. But what you see happening after a few seconds is a collapse of traffic because humans are not able to maintain distances. This is the cause of a lot of energy inefficiency in traffic. 10 years later, a Cal grad, Denmark, did this experiment. The arrow is its self-driving vehicle. Right now, the car is just driven by a human, and you can see after a while, the same oscillations happen. Now we're going to engage the autopilot. Okay, now it's self-driving, and what do you see? Suddenly, things smooth out. 42% energy savings with that algorithm. And that's an interesting paradigm because this is the beginning of a new era. Now, let's do 2 lanes. You can see this guy is behaving kind of like a jerk, right? It's switching lanes to prevent people from passing. But it actually stops the problem. The computer learned to do it with machine learning in a few minutes. And you could argue, well, what's the big deal? You learned this in police academy, right? Okay, now try this one. So now, what did the computer learn? It learned to create a snake. It learned to do it without any model. It's just artificial intelligence. Now this, I can't tell you what it's doing anymore. It sometimes will hold cars, sometimes it will let them go, but I can't even rationalize what it came up with. But you look at the numbers, it's actually more efficient. So where are we going with this? What about the Bay Bridge? There's right now a big metering light that prevents cars from entering. What if instead you had self-driving car holding the flow so it flows smoothly? This is a reality we will collectively experience within less than 10 years guaranteed. And artificial intelligence enables us to solve much more complex problems, such as closures created by truck accidents. So hopefully this gives you a glimpse of what the future might look like.
Okay, so if you're interested in this type of work, mixing AI and other algorithms to fix the traffic problems, feel free to contact Alex or list his capstone. Okay, see who's next. Do we have anyone on Exabiome? Yep, okay.
Hello, everyone. So my name is Ben Brock. I'm a PhD student here, and I'm going to talk about some of the work that my group is doing. So I'm advised by Kathy Yellick and Aiden Bullock. So if you're interested in this kind of stuff, you can contact either of them or me. So our group primarily does high-performance computing, or supercomputing, which is the problem of writing programs and building programming systems for people who want to write programs for large clusters of computers. For example, the supercomputers that we have up on the hill at Lawrence Berkeley National Lab, one of which is ranked as the 12th fastest supercomputer in the world. And one of the applications that we're focused on is genomics. So what is bioinformatics or genomics? The general problem is you want to get the DNA that's inside, a human or some kind of species. So you use a physical sequencer to extract little strips from that DNA with some error rate. And then you need to use computer algorithms to reconstruct them. And so this is a really important problem for health, for the environment, for all kinds of applications. And there are even further applications where you want to look at, for example, someone's gut or soil, and you have lots of different microbes that are mixed up together. And you need to have really great processing power in order to successfully reconstruct this so that you can have the actual genome that you can do analysis and make scientific and biological advances And that's why we're interested in it. There's a big project related to this and creating softwares for supercomputers so people can do this kind of data analysis. Now, why this is interesting to us as computer scientists is basically there's this big pipeline with lots of different applications and distributed data structures that are interesting case studies for the kind of problems that we like to work on. So I, in particular, work on distributed data structures and on hash tables. And so we're looking for people who are interested in taking some of the work that we've done and extending it and applying it to different areas in genomics. And using this, we've already been able to make a lot of advances, like assembling big genomes that no one has been able to assemble thus far. So thank you, everyone. That's all I have.
Okay. Yeah. So there's more slides if you want to essentially take a look. Now, let's see how to make DNS faster.
Right, thanks. So this is I'm a postdoc with Kurt Ketzer, so this is from Kurt's group. There's 3 MNG projects. We had very good success last year, very good MNG students. We had a very high impact paper submitted 2 months ago, and the MNG students who work with us, one of them got admitted to UIUC. He's going to do PhD there. The other one started a startup, and the third one is now going to go to Google. So we thought, let's expand this project, and we're going to have 3 MNG Capstone projects. The first one is related to squeezing deep neural networks. So we want the accuracy of deep neural networks, but with constraints on power and energy. So we have the autonomous driving. So for example, you have Teslas or other companies that are making autonomous driving. You cannot put a DGX1, which is the latest hardware from NVIDIA, in an autonomous vehicle because it's going to use 3K watts of power. But even if you do that, you cannot put a very accurate neural network because if it takes 1 second for the neural network to process an input image, it's not enough. If you're going 60 miles per hour, you need to, for example, give the result in 10 milliseconds, whether there's a car in front of you or not. And another problem is, for example, if you look at the phones, for example, Apple phone, there's several neural networks in for example, when you're talking to the phone, you cannot put a very big neural network because you don't have enough memory. And another very exciting thing is smart cities. So we know 5G is coming, and in smart city, every traffic light is going to have a 4K camera, and they're talking to each other using 5G technology, and you cannot, even with 5G, stream 4K video in real time. So the idea is that Verizon and Nokia and other companies working on smart cities want to perform a lot of compute at every intersection and only send partial results. So that's where squeezing these AI or neural network becomes very important. So the idea is, what can we do with 100x less power without losing accuracy? So let me skip this in the interest of time. So this project is going to be related to Squeeze AI. It will involve designing compact neural networks. By design, they're small, but they don't lose accuracy. It will involve some work on hardware-aware co-design and quantization. So quantization is, for example, when I write 0.1 in Python, it's represented as 32 bits. So basically, 21 bits for mantissa, 10 bits for exponent, 1 bit for sine. But do I need 32 bits for saying whether this is a cat or a puppy dog, or whether the car in front of me is stopping? Probably not. So I can reduce the bits. But if you do this naively, you're going to lose accuracy. There are methods, we are collaborating with Professor Mahoney's group on using second-order methods that would allow you to quantize the bits such that you can run these neural networks very fast. And this is an image of a RISC-V architecture that was designed in Berkeley. This is going to be an open source CPU. The cost is going to be an order of $10. So $10, think of an open source hardware. And this processor only has 3 megabytes of cache. So your neural network and all of its memory footprint has to fit 3 megabytes. And this is something that we're targeting to design accurate neural networks that can fit on this chip. And this is going to be a very high impact project. The second project is going to deal with large-scale training of neural networks. I think this slide got skewed a little bit. So Tesla has about 1 billion hours of training data. They're collecting data every day. If you see all the Tesla cars, they have 8 cameras and a radar. They're collecting all the information, velocity, GPS information, and how the driver interacts with the car. But they cannot train on 1 billion hours of data. Even on the biggest supercomputer, if you want to run these things, there are very intricate details that a typical data scientist is not familiar with. And it touches base on how you communicate this information efficiently such that when you run it on a supercomputer, let's say 100 GPUs, it scales with 100x. So your speed up is 100x. So there is an interesting race between different giant tech companies. There is a benchmark task called ImageNet training. It's a classification image. I give you an image, and I want to say whether this is, for example, a specific type of dog or a specific type of car. And it has about 1 million images. Training data is 1 million. And it takes 700 hours to train this on a single GPU. So 700 hours, 2 years ago, this was the time. In 2016, Forrest Yandola, a former student here who actually founded a startup, designed Fire Cafe and reduced this training time to just 10 hours. So 70x, or about 10 hours on 128 GPUs. And then Google followed, Amazon followed, and Facebook 2 years ago released a number where they were able to do this training in 1 hour. So now think about Tesla. They have 1 billion hours of training data. If you can design a method that can efficiently train on this data, it's going to immediately impact what they're putting on, in their AI engine. And then in 2017, a student in our group, Yang Yu, who works with James Demel and co-advised with Kurt Koitzer, was able to reduce this to just 15 minutes. Very significant result. And then we followed up and we collaborated with Professor Mahoney's group using second-order methods. We designed an efficient method. And Sony, 2 months ago, used this method to do the training in just 2 minutes. So going from 700 hours to just 2 minutes. So now you can imagine what our big companies can do with this. They can, iterate over design and, find better neural networks. They can do very fast hyperparameter tuning. So this project is going to involve development of training methods for neural networks at supercomputer scale. You will have access to the Cori supercomputer in Lawrence Berkeley National Lab and probably the Summit supercomputer at Oak Ridge National Lab, which is the top supercomputer in the United States. It will involve exploration of efficient communication avoidance schemes at scale and fast neural architecture search to automate search for quantized neural networks. So there will be a lot of talk with the first group that will be working on the quantization work. And then there is another very exciting project called natural language processing with deep neural networks. If you're following the news, OpenAI 3 weeks ago released the new AI engine called GPT-2. This is very exciting and a little bit scary. They took all the Reddit posts, so they searched Reddit, and they downloaded all of Reddit, and they trained a neural engine such that it can learn language semantics. And then once they train it, they would give it an input sentence, and they would ask this AI engine to think about this or come up with some response. So they gave it this input: recycling is good for the world. And this is what the AI engine wrote. No, capital letters, no. You could not be more wrong, double exclamation points. All of this is done by the AI engine. It's very, very scary. And this is its reasoning. Recycling is not good for the world. It is bad for the environment, comma. It is bad for your health, and it is bad for our economy. I'm not kidding. Recycling is not good for the environment. And then it starts to reason one by one. It is destructive to the earth, and it is a major contributor to global warming. Recycling is not good for our health. It contributes to obesity and diseases like heart disease and cancer. Recycling is bad for our economy. It increases the cost of a product, and in turn, the price of everything that is made with that product. Even it's wrong, it's so scary. It's reasoning very well, and it's learned a lot. So this was a very significant improvement. Ilyas Eskiva, actually the CEO of OpenAI, was here this week, and we talked a little bit about him. This is very intricately connected to that large-scale training. They trained this for 2 weeks on 100 Volta V100 GPUs, and it's very scary. And actually, OpenAI didn't release the model because there was a little bit of worry about fake news generation like this. But we want to use this for performing NLP on device. So this model is really big. This is like 5 gigabyte model, a ginormous model. You would like to use the same technique to design client-centric NLP such that when you perform, for example, you talk to Hey Siri, what happens right now? It gets your voice, it sends it to an Apple server, performs the inference on the server, and gets the result back to you. You would like to do that on your phone because of privacy reasons and because sometimes you don't have connection to internet. And then this can be applied to a car as well. You can talk to your car without having this 4G or LTE connection. And this is going to touch base on a lot of topics on NLP like sentiment analysis and multi-label classification, and you will learn a lot about different things in NLP. So if you're interested, definitely email us. It's best if you want to find the right project in general. It's good that you reach out to the people who are presenting here and say, hey, I'm interested in this. This is my email address, amirgh@berkeley.edu. Feel free to email me and say, hey, I was maybe interested in this. Can I learn more? I would be more than happy to talk to you about that. 3 projects: Squeeze AI, systematic quantization of neural networks. The proposal for this first project was rated #1 in the whole bakery area research. So we have made very, very good improvements here, and it's very promising. So if you're interested, we have a lot of resources. We're working on that. Large-scale training of neural networks, our group has been, I think, a leader in that field. And we have a very exciting project where you'll be involved with working with different supercomputers. And NLP with deep neural networks is the 3rd Capstone project. And if you're interested, definitely send us an email. Thank you.
Okay, Gerald.
Hi, so my name is Gerald Friedland, and I work in an interesting mixture of different jobs, which is also for you an advantage, because if you want to have some context to Livermore, it's another national lab, or to smaller private research institute, non-profit too as well, International Computer Science Institute. I'm here. Also, Mike Mahoney is working there too. In any way, so I do a bunch of things from very practical to a little more fundamental, and it started all with this. We collected from Flickr 100 million images, 100 million videos, 100 million images and a million videos, and they're all on the cloud with various annotations and benchmarking results. And the idea was that you can go, and now instead of like Darwin, who just went and visited the birds in remote islands to do the studies, you can just go and say, hey, we have a real-world reflection in these videos, because we can study how people live, or how people's habits, or whatever science you want to do in these videos, because YouTube and all these we have so much recordings of the real world that we should just analyze those and can have a bunch of research results, right? And the idea is, yeah, good, but the problem is how do you actually find the videos that are relevant for your research? And this is basically what this is about. So we built a bunch of tools, and we have very good connections to Amazon. And we built a bunch of tools together with Amazon, sort of put this into all the data science realms. So this is a Jupyter tool where you can just go ahead, for example, upload an image, and it will automatically tell you where similar images are located in terms of location, geolocation. Now this, for example, can be also used to try to do fake news detection, right? So if somebody tells you, this thing happened there, and it turns out that image is actually not from where they say it is, here we go, we have some fake news detection. That's actually a project that's also starting right now. So this is there's a lot of interesting practical work that can be done. And one other anecdote is I had an undergraduate student coming to me. I want to work on origami. It's like, okay. I didn't know anything about origami, but the person went and said, okay, here's what I hate about origami. I hate that there's all these instruction videos, and they say it's really easy, and then I try it, and it takes me 3 hours, despite the fact that I've been origami for many years. And so he wanted to create a new scale of difficulty for origami based off of learning from comments and also from the videos. And then he did it. He actually created some machine learning that created a new scale. It was very hard for me to say how good that scale is, but what he did is, don't worry about the professor, just submit it to the origami conference. He did. He got accepted, and they all agreed we should change the scale. And he got an award for it, and he got a bunch of other things as well. I'm not sure if he's still working in origami for real. I think he has a job that pays a little more. But the interesting thing is try to influence something like the Origami Society, all possible with sort of interesting projects on these videos. Now, another problem that we had is you have sometimes these results in machine learning and you don't know what they do. And so the work that I do at Livermore Lab is sort of finding out, can we make this more explainable, both qualitatively, as you might have seen many, for example, these are handwritten digits called MNIST. Probably have heard about those. And the question is, okay, so this 2 on the left, how much of a 2 is it actually compared to the other numbers? And you see it's kind of a 2, but it's also a 4 and a 9. And the same goes for the 3 and the 5. So this is kind of qualitative explainable AI. And I know that there are other groups here on campus that do this as well. So there will be a way to collaborate. The other thing is I went to Amazon again and said, we need some more budget for these deep learning experiments. And they came back and said, okay, how much money do you need? Which is a good thing. The bad news is I couldn't answer. I didn't know. It turns out if you look at the current ImageNet experiments, there's 2 orders of magnitude difference between the size and also the training time of the network. And so it does matter whether I ask for $10,000 or whether I ask for $1 million. It's like, you need to be better than that. Like, if you have 2 orders of magnitude, anything better than that will be easy to do. And so we worked on this basically trying to find out kind of capacity measurements for neural networks. And we have a demo on this if you want to try this out. And also we're using these now, and I have a research seminar at 294 on where we're trying these out for various multimedia tasks. For example, the question was always, why do these deep neural networks have the huge convolutional layer? Can we replace this with something that we know better? For example, JPEG. And turns out you can. Just use JPEG, and you don't need a deep convolutional layer. These kind of experiments we're trying to do. Yeah, I think that's my summary. And if you join the group, then there's all kinds of things in either the practical part or the more fundamental part that can be done. And I'm looking forward to talking more with you later.
Okay, Carl. Great, thank you. I'm Carlo Séquin, and these are the kind of shapes I like to build. Now, much of the research in computer graphics today is focused on creating ever more sophisticated renderers. On the other hand, the tools to create geometrical and graphical content seem to evolve much more slowly. So this is a software engineering project, and its goal is to make enhancement to computer-aided design tools for complex geometrical shapes like these that have a high degree of symmetry. The inspiration for this project came from this small sand-cast bronze sculpture done by Charlie Perry. He is an artist very famous at the east coast of the USA. I found it rather difficult to design something like that using SolidWorks or Blender or Maya. So this is the CAD tool that I would like to have. The overall symmetry of the border curves that you see in this structure is most easily described in a procedural manner. But how the surface connects to the various branches on these borders, that is done much more easily through interactive computer graphics. Fine-tuning of the geometry through the whole process should be able to be done by a few sliders that change aspect ratios and change angles and the like, and those sliders should remain active all the way through the very end of the design process. Now, the key challenge is that any changes that you make interactively in the graphics environment should be fed back and incorporated as seamlessly as possible into the original high-level procedural description, and that's the real challenge. Recently, I have been interested in thin, smooth surfaces which may be, however, single-sided or non-orientable, such like the twisted Mobius band or a Klein bottle. Thus, we have started to construct an exploratory tool aimed specifically at such shapes. We call it NOME, for Non-Orientable Manifold Editor. And here is an example how this should work. We start writing some simple procedural code that defines 3 circular loops and then combines them into this triangle configuration that you see on the left. Some more code then takes 10 of these and intersects them in this tangle that has icosahedral symmetry. And perhaps it also places some markers that show the 3-fold and the 5-fold symmetry axis that this object will have.
Then in this graphical display on the right, we can now click on some of the vertices on the curves and introduce some interconnecting faces. Because of the 30-fold symmetry of this object, we only have to do it for one of the lobes. And then the procedural definition takes over and produces 30 identical copies in the proper places. In the center picture, you see an example of one of these outer lobes, and this gets then replicated 30 times, put in the right place, so we then result with the configuration on the right. GNOME then offers a couple of sliders that tells you how much smoothing you want to introduce into the surface and how thick you want to make the offset surface that then goes through the 3D printer. And in the whole process, all the sliders that define any of the geometry should remain active, so that the designer can actually fine-tune the shape in this very final form, properly thickened and smoothed. And this then is what may come off the 3D printer. We have a timid first demonstration of this. GNOME is still brittle. It needs clearly more capabilities. For instance, I would like to have real minimal surfaces that you can find in soap films. I also would like to introduce some volumetric primitives. But most importantly, GNOME needs to be implemented in a robust computer science software engineering manner. I think this makes a good master's project for a small team of engineers. Some of the graduate courses you would have to take would be in advanced computer graphics and in software engineering. And my office is 639 Soda Hall. If you have more questions, then you're welcome to stop by.
Hello, everyone. All right. My name is Alan Young. I'm the faculty advisor for the Capstone experience for augmented reality and virtual reality. So I brought a whole bunch of stuff in here. And I'm going to give you, in the next few minutes, I'm going to give you 3 reasons why probably you want to choose, first, come to Berkeley, make sure. And second, choose AR and VR as your capstone project. So the number one reason is probably, if you come to a university and take graduate courses in the 80s and 90s, probably these, in EECS, these are the things that, technology you want to study to make, new, products happen. Now, if you go to a university in the 90s and the 2000s, the technology that will make these things happen will probably be, the subject that you want to study. Now, fast forward that we are in 2019, and by the time that you graduate will be 2020. I think it's a high time that we find something that is revolutionary, potentially can replace these things. Why don't we take a risk and, and try to see if we can make AR and VR to replace the traditional computing paradigm. So this will be the revolution that if you want to start new business and you want to start a new research experience that is different from your undergrad project, so that could be an area that you start with. Now, having hope is not enough, right? So we need to have some solid stuff in order to really commit to 1 year research, because 1 year is not too long, but it's also not too short. So I'm going to give you 2 other reasons. Number one is that, so we have offered this AR/VR experience for 2+ years now, and if counting the lead time to build up the infrastructure to enable students to do research is actually longer than that. If you come to Berkeley and choose AR and VR first, we will have very good facilities and resources for you to call home. So in this case, we have the Virtual Reality Club. We have more than 200 undergrad students study AR and VR. So if you don't know anything about AR and VR, but you just have a strong interest in that, we have the so-called decal classes to teach you C# programming and how to program in AR and VR. And then we have 2 institutions. Number one is the Jacobs Institute, was donated by the founder of Qualcomm and Paul Jacobs. So it's focusing on research the combination of engineering and design, the 2. The Jacobs Institute, it's a new building. It's a state-of-the-art facility in here. And we also have the Vive Center, which is in Corey Hall, was also donated by HTC Vive. It's one of the leading companies in virtual reality and also in augmented reality. So you can actually use those office spaces and talk to the students and researchers in those areas. And we also have a one semester graduate course, CS 294 and 137. And if you want to do AR and VR, there's a lot of moving components. So in this class, we're actually trying to, in one semester, to give you really fast up to speed. Three professors in graphics, computer vision, and human-computer interaction. Now thinking about finding jobs, our program also has a very good visibility in the industry. So our sponsors are not only including Qualcomm and HTC, but also Siemens, Intel, and Ford. And in fact, talking about Intel, we are actually the only program in the Bay Area that is currently having a research grant from NSF and Intel study AR and VR. So that's the second reason. The last reason is, choose a program. So we have two projects for you to choose from. The number one project is called Open Art. So let me see. Oh, I don't know how to play. Okay, so this one doesn't play. Okay, and okay, so that's okay. Okay. So I actually want to play this video first. So if you choose Open Art, one of the projects we're working on right now is that we actually have an ambitious plan to scan the entire Berkeley campus and move that into a CAD model. And so it's going to be 1-to-1 ratio and millimeter accuracy. So we have the hardware, and we want to develop the right hardware and algorithm to turn the entire Berkeley as an AR/VR hotspot, right? So if you are a company and then you want to test the latest AR/VR devices, we have the entire Berkeley, under your proposal. And when our students are not, busy working and finish homework, we actually have some events and that we also wrote into Open Art that use a single depth camera to actually monitor your deformable body. So this is not a skeleton. It tracks your body particles. So potentially you can actually augment a virtual shirt. And our program is rigorous and also fun. And because of that, in the past, actually last year, we actually won 2 of the premium awards. One is in the US. This is the Microsoft Imagine Cup. I think it's the #1 entrepreneurship competition in the US. And we also won the gold medal in China, the 2008 the Internet Plus entrepreneurship competition. And the last project you can choose is called EECS. So this is using AR/VR to control drones. So it actually allows you to have Iron Man vision that you can actually control multiple drones flying in the air. If you are not familiar with the robotics and drones, you should actually go to YouTube and search Amazon warehouse mothership. So this is a concept from those companies that are trying to use drones to deliver products. So imagine in the future, we're going to have a lot of drones flying in the air. How do we do area control, right? Area traffic control. You're not going to be flying the drones by yourself. So our interface that we built enable you to use virtual reality and oftentimes augmented reality to be able to control those drones at the same time that it's actually make the human capable
Here's
of
the
doing
3D
that.
mesh of
So
our
this
lab
is
in the
actually
Unity
the
interface.
lab that we have,
Users can
and then we
zoom in
can
and
actually
out
right
to
now
get an
use
overall view
a
of the
single
scene.
virtual reality system to control
Outside of the
multiple
scene,
drones.
there are 3 menu bars.
I know that you guys have
Users
access to
can
this
rotate a
slide,
scene
and
by
due to the time
controlling the right
constraint, so
thumbstick.
I will stop here. And if you have any question, our Vive Center is in 3rd floor, Corey
can
Hall.
also move
You
forward
can write me
and
emails,
backward
and you can
using
just
the
knock
left
at the door,
thumbstick.
and then if you have any
To
questions.
complete a
Thank you.
task of climbing hoop jump, we set 2 hoops and 2 drones in the scene. In a
Okay. Eldon.
Thank you, Vladimir. So I'm Eldon Schoop. I'm a PhD student working with Bjorn Hartman. And this project may be a little bit different than the other kind of like longer-term research projects that you've heard from the rest of the groups. This one, it's much more focused and tied in intimately with the Jacobs Institute, which I'll talk a little bit about. So Berkeley is basically at the very forefront of tying together making, fabrication, and prototyping with engineering education. In fall 15, we prototyped and we launched this program called MakerPass, which gives students access to like over 30,000 square feet of like state-of-the-art fabrication spaces and an ecosystem of design classes and design specialists, which enable people to create rapidly physical hardware prototypes, get access to design support, and take classes in our buildings. The system, in order to grant access to the spaces, collects a bunch of data, including training for the equipment, like access control and reservation systems, most of which we've actually built in-house. And just to give you an idea of like the scale of this data that we're working at, I mean, it's not, you know, ImageNet sized, but this semester we have over 1,200 students registered in the MakerPass system in over 40 different spaces and equipment types. And so we started asking ourselves last year, like, okay, we're sitting on all of this data, what can we start doing with it? So we just did this quick exploratory analysis with a system that we called MakerLens. And immediately, this resulted in direct impacts to the operations in Jacobs Hall and in the MakerPass program. So for example, we learned something that, like some of the things we learned, let's say about 43% of our students in the MakerPass system are responsible for driving utilization up to 100% at the end of the semester. Over half of our student community in MakerPass is new every single semester. And these are stats that, you know, we're just waiting to be discovered, you know, waiting to be unlocked from the world that, you know, we had no idea about, and immediately let us plan for future semesters and impact the operations and day-to-day student experiences in the MakerPass program. We also published a paper in this conference called ISAM, the International Symposium of Academic Makerspaces, which is a joint effort created from MIT, Yale, and UC Berkeley, and Olin College as well, which enabled us to open source our tools and share them with the making community as well. So kind of having an impact there on allowing other universities and private makerspaces to get the most out of their space and help people prototype their ideas. So what this project is proposing to build a production level system on top of these like exploratory analytics so that we can not only have greater impact at these making and academia conferences, but also release tools for the open source community to help others improve and run their spaces. So this consists of, you know, developing and productionizing a real-time analytics dashboard. So for example, taking the data from, you know, our registration, our training data, our access control data, and equipment reservation, and coming up with, you know, granular insights that staff at Jacobs Hall and other makerspaces on campus can use to make day-to-day decisions. And then using that as a platform to then prototype and implement kind of real-time streaming ML to answer questions such as, well, when might we need to maintain equipment based on use? Can we predict when equipment might fail? Can we predict when we need to allocate different staff members to account for the peak in demand at the end of the semester? And essentially, like using different models to help run our makerspaces and help streamline our operations and improve the day-to-day of our students. So I think this project is particularly exciting because it kind of combines two different lenses within the work itself. So there's this kind of academic research context in which you get to kind of rapidly prototype and evaluate an engineering project, and you get to prototype a lot of different models which can work on all this data that we've collected. And it also gives you the opportunity to work a case-based kind of almost consulting type project in which you can directly have an impact on the way that we run Jacobs Hall here at Berkeley, and also have an immediate broader impact in the academic making community. So I think it's a pretty exciting way to combine these hands-on skills in which you can get to prototype software, get to manage this project, and also have an immediate impact. So feel free to email me. I do work in the Berkeley Institute of Design, which is in Hearst Mining, and also in Jacobs Hall. Thanks.
All right, well, thank you. So, what do I hit this one? So my name is Michael Mahoney, and I'd like to tell you about a couple different projects. Amir Ghalami, that gave the talk about 10 or 15 minutes ago, gave you sort of an inkling about how some of these things might be used. And you've heard a whole bunch of other talks about sort of downstream applications that are pretty interesting. So I want to look under the hood and say, you know, how do these things actually work? So a lot of machine learning and data science sort of tools under the hood involve matrices and optimization and this sort of thing. And so oftentimes there's a lot of little subtleties to get things to work properly. And so I want to tell you about two sort of related projects on something called second-order optimization methods. And if you know anything about second-order optimization methods, We're going to be using them just in very different ways, and that's because the way these things are used in a lot of machine learning and data applications is very different than how they've been used historically. So one is some sort of second-order optimization for neural network learning, and also designing adversarially robust neural networks. And so what you should have in there in the back of your mind is if you have a self-driving car application and you're going down the road and you see a stop sign, it's not so good if I can change some minor structure in the image of the stop sign or minor thing in your pipeline to make that look like a yield sign, for example, or a goes full speed ahead sign. You can imagine that's going to be a problem in a lot of use cases. And so there's some subtleties here that are pretty interesting and will lead to a whole bunch of projects. So training neural network models is hard, right? So there's a huge number of people that are paid a lot of money in Silicon Valley to fiddle with hyperparameters. So what do I mean by this? So the landscape of optimization is there's sort of first-order methods, which basically are gradient-based methods. Think of a Taylor expansion. It's a gradient. There's a leading order term. And those are good, but if things are sort of round and nice, but not so good otherwise. And then there's second-order methods, which take advantage of Hessians, the next term in the Taylor expansion. And those are very good to get high precisions, and they're totally ubiquitous in scientific computing. If you design airplane wings and fluid mechanics and sort of stuff, fluid flow simulations, you'd use those. You wouldn't even touch first-order methods. That's not used in data science, and I think it's just because second-order methods, Hessians, are a little bit more complicated to think about than gradients. People, even if they don't have a good intuition about what goes on in million-dimensional spaces, think they do because gradients, how hard can it be? You just roll downhill. Whereas Hessians, are just a little bit more complicated, and so people don't use it. So the 99% use the one, the 1% use the other, and then the latter gets swamped. So when you have a problem with that paradigm, what do? And so a common MO is to say, tack on Band-Aids. And the way you parameterize Band-Aids is you put a parameter in, and then you say, I'm just going to do a hyperparameter search. And when that doesn't work, you tack on another Band-Aid, and it'll do another hyperparameter search. And this is why you spend an enormous amount of CPU effort and GPU effort to sort of cross-validate those. And if you don't know anything about statistics, you're going to want to cringe now because false discovery, and you're probably going to overfit and be extremely brittle and non-robust, and that's in fact the case. So training neural networks is very hard. The algorithm might be slow. That could mean CPU or GPU time. It could also mean that you spent 5 months fiddling with your hyperparameters, and the actual algorithm takes 10 minutes, which is actually the more common use case. I actually feel like that guy in the third bullet there sometimes when I'm trying to get code to compile. And so do you need a faster solver? So one of the use cases for second-order methods is if you want a faster solver. We have some some projects along those lines. But what I'm going to talk about today is not those. It's something more along the lines of the first three. So under the hood, the way these algorithms work, and I have a picture here of something that's almost convex. Is this the case in a lot of machine learning applications? And so in a lot the answer is yes, and in a lot the answer is no. And so you might use first-order information, which in this expansion is G, a gradient. It's a vector. You might use second-order information, the Hessian. And the sort of thing you'd do if you know anything about this is to say, the Hessians are more expensive, and so there's a footprint of cost to compute, but you just converge much faster in terms of number of iterations. So now the computational model is a little bit trickier. You're saying I have sort of a cost to approximate a Hessian. You never need to solve linear equations. If anyone says don't use Hessians because you need to solve linear equations, walk out of the room, because you don't. To compute an inverse. You never need to compute an inverse. You just need to get an approximate solve to the linear equation. And so can you get away with a very low quality approximation there, for example? And so that's something that might be of interest. And so the Hessian is going to be more expensive to evaluate, to compute, to write down, but you don't necessarily need to do that. You can get some sort of approximation. So we have a lot of theory along those lines. And you might say, how does a theory work? Here's a very practical problem. I use my first-order method. I use my second-order method. I have a curve that looks like any of the following. Say it looks like the one on the right, and say it's the yellow. I go over a little bit. I go down. This is a log scale, so I actually go down a lot, and then I'm flat. And the x-axis is log scale. So orders of magnitude. I'm flat, I'm flat, I'm flat, and I'm flat. I'm right there. So I'm flat. Should you stop? Right? Should you stop? Or if you run another week, are you going to get a better result? And how do you even answer that question? So in some cases, the answer is yes, and in some cases, the answer is no. And so how do you answer that question? So can you develop tools to try and answer that question? So the answer is yes. So we have tools to sort of do that. This is very different than the way these things are used in convex theory. So this is a very different use case. Second-order methods may be able to escape undesirable saddle points in very different ways. Low communication costs in distributed setting, right? There's a fixed footprint of cost, but if the pain point's the communication per iterations, it may be much better. Computational advantages by putting them on GPUs. We have a bunch of results along those lines. And the abstraction when you're working with data is, it's a very leaky abstraction. It's not like you have a subroutine that you call like a usual sort of model you might have in computer science. It's a very leaky abstraction. If I get an approximation to a result, that's a very leaky abstraction. And so you might get a better result by getting a lower quality answer, sort of an implicit regularization. And so we see that also. So we have a couple different types of projects. Since we're looking under the hood to see how the engine works, we have 3 wheels and they couple together to make everything work. And so what we're doing is an algorithm. We do some sort of iterative update, and we have a couple things that are very different than the way these things are used traditionally. One we want to call, let's say, interpretable training, adversarial robustness, and very low precision quantization. So interpretable training. So these are, on the bottom, some sort of results that we've had in the last year or two, and the sort of immediate next follow-ups. Hessian-based analysis of large batch training and robustness to adversaries. As you're training, how does the penalty surface actually look for realistic neural network? And it's actually rather complicated. And how does this behave as a function of batch size? So a lot of people just say larger batches are better. Why? Because, how can it be worse, right? You have larger batches, it's good for throughput, it's good for latency, it's good for some sort of reason. And so, you want just larger ones. And in fact, the larger batches, this is an endogenous regularization parameter. So smaller batches might be better, statistically. They might be worse computationally. How do you look at that trade-off? And that's a very non-trivial space. And so we have a couple results characterizing that, where large batches are actually worse, and there's a trade-off point in between. Not obviously, but working with batches of different sizes and or adversarial data, you can smooth out this penalty surface in very non-trivial ways. So the usual story is my penalty surface is sort of a little bit choppy, and so I should use a second-order method to find the right direction. One thing we've seen is that if you train to adversarial data, you smooth out the penalty surface a bit so that second-order methods can be used fruitfully. So that's a little bit strange if you know anything about classical theory. And the reason is, I think that if you don't use that and you just train with the usual MOs, the surface is just too choppy. You can do nothing except add a massive amount of gradient noise, which is what just low-precision sloppy SGD does. So sloppy gradient descent does that. And so if you smooth out the surface by fitting to adversarial data, then it's not obscenely choppy, it's just very choppy, and so you can use second-order information fruitfully. So we have a bunch of examples like that, and there's a bunch of low-hanging fruit extensions along those lines. Adversarial robustness. So you don't necessarily want adversarial data because it's a bad thing, and it turns stop signs into yield signs, so you want to be robust against that, and there's a range of people who ask that question. A different question you can say is, can I use that adversarial data to get a better model? Not to defend against adversaries, but to train better, for example. And so Amir gave you that chart down and to the right, and you mentioned the Japan group. They used a result that we pushed out about a year ago to say, I can smooth the penalty surface, and I can train ImageNet in a minute and a half, or whatever their record was at the time. And so very different than the way these things would be used, but exploit adversarial robustness in a very different way, to defend, to construct attacks, or just to smooth out the penalty surface for purely computational reasons, and because you get better statistical properties as a result. How else might you want to do this? You might want to quantize. Why? Because you want to put this on your cell phone. So how do you quantize it? You have 50 different layers, and how are you going to try and understand how to quantize it? So if you have 50 different layers, can you look at some sort of Hessian structure as a function of those layers and say, I quantize this layer, do a little bit of retraining, and then that second layer. And so you can use second-order information, which captures correlations between that, to do blockwise quantization in a different way, and we have results along these lines. So there's a bunch of different results we have there, and that gives you 3 different examples, but they fall sort of under a couple different types of umbrellas. So if any of those seem sort of interesting, let me know. My name's Michael Mahoney, and I guess my name's not on this last slide. I had a final slide, but it was pulled from the slide deck, I guess. I was going to put up the slide. I gave this talk, a year less mature version of this talk a year ago at your colleague's predecessor's T-minus a year, and so I actually had a slide up of a paper that we put up maybe about 2 weeks ago, exactly characterizing the second-order information and how the scaling does and doesn't work when you get to larger batch sizes. So this was an example of some students who were in your chair a year ago and hooked up with us, and we got a very nice result, and there's some follow-up directions we're actually looking at right now. So send me an email. Since I don't have the email on this last slide, I'll go to the / Michael Mahoney. Ping me if you're at all interested, and it would be great to have you, I guess, 1 here at Berkeley, and 2, understanding what's going on under the hood.
Hi everyone, I'm Utkarsh, and I'm a graduate student working with Professor Ren. He was unfortunately unable to come today, so I'll be presenting instead of him. And the project that I want to present about is called OzVision. Like, the one-sentence summary of this project is that we're shooting lasers into people's eyes to show them colors that they've never seen before. Now, that's a lot to unpack, so I'll like step through this one by one. The thing that you see here, it's a beautiful device. It's called an AOSLO. It's just a very fancy eye microscope. So it looks at the back of your eye, it looks at your retina, and it has good enough resolution that it can see, like, it has cellular resolution for your retina. So, you know, if your eye were like a camera, then it could see all the pixels in it. And not only can it see those things, it can also like put in arbitrary patterns of activations. So it can stimulate them in arbitrary ways, however you want. So for example, if you wanted to project a pixel-perfect image of a dog onto someone's retina, we can do it. And what we want to do is that we want to apply it to understanding color and, you know, like trying to generate new colors. Whenever people usually talk about colors, usually what they have is, you know, they have this color gamut. So basically, these are all the colors that you usually see. The edges of this horseshoe are sort of, you know, the pure wavelengths. And whenever you have a projector or a screen, it's usually a very small subset of it, the small triangle that you see in the middle. And so if we just carry out the math, the kinds of colors that we should expect to see, if we had access to all the arbitrary combinations, then we would expect it to look something like this. So in the ideal case, if everything works, we would expect the gamut of this new Oz display to be actually bigger than the colors that occur naturally. And so, for example, one way of explaining it is that you have 3 types of cone cells, kind of like RGB pixels, but 2 of those types have very similar sensitivities, right? So, for example, the green cone cell, they never really activate by themselves. They're always almost always they have co-activations with either red or blue cells. So if we were to just activate the green cells somehow, then we should expect to see a really, really saturated green color. And we're still doing experiments on it. We don't know exactly what's going to happen, but this could potentially be a cool experiment, right? Another potential application of this is for studying color blindness. So in 2009, people did an experiment where they took some colorblind monkeys and they used gene therapy to like randomly modify some of their cone cells to express a third type. So, you know, now like these adult monkeys who had always grown up with only two types of cone cells had suddenly a third type of cell. And the scientists found that these monkeys learned to use the third type. They could now differentiate between colors that they were unable to differentiate between before. And so the question is, can we replicate this in humans? Well, humans really don't like getting injected with like viruses in their eye that like mess with their genetics. But using our machine, we can try to simulate this whole experiment in a completely non-invasive way. And so, you know, basically you would start off with 2 types of cone cells in a person. You would randomly modify them, or at least you would pretend as if they were randomly modified, so you could pipe in an RGB information in such a way that the person is like, their cone cell activations would sort of mirror the cone cell activations in a normal person. And then we could try to see if the human learns to see a new color. And again, just to recap, basically, you know, we have a laser scanning on the retina. We could potentially see colors that are impossible in the real world. We could potentially look into color blindness, and we could potentially look at higher dimensional colors. In general, we want to use this as sort of a platform just for neuroscience experiments, because what we really have here is a very high throughput input into the eye and into the brain, right? So we want to see what exactly goes on at the very edge of our perception. And this is where we need your help. We need to build basically a very, very low latency, very high throughput system that is doing image-based tracking like at 1,000 hertz. It can at most have end-to-end latency of like 1 millisecond, and it's targeting like 10,000 of your cone cells. So we need to build like a very high performance system. And like that's where you guys come in. I can talk more about this during the breakout sessions because I don't have much time here, but yeah, that's it. Thank you.
Okay, let me skip this for now and we'll come back to it. Brian is around. I saw
him. Okay, so maybe I'll do mine and come back to theirs. Okay, so machine learning, we've heard a lot about it, and interestingly enough, it's also applicable to circuit design. So for those of you who are in the Phi Inc. area, but also in DSS, this is an interesting project that combines the two to do essentially rapid circuit design. Today, if you look at how circuit designers have to design their circuits in advanced processes, they have to actually go immediately all the way and consider the layout of the circuit because of a lot of parasitics of the wires between transistors. So that is a very tedious process. Imagine that for every design instance, you have to go and create an image of it, a literal image, polygons, do the extraction, see what the parasitics are, and then understand how well your design works. That forces people to really think very carefully how to parameterize these designs in code. So we have tools that have been developed at Berkeley, are called Berkeley Analog Generators, can help you as a circuit designer to codify in Python how your parameterized circuit layout looks like. Once you have that, you can either go and take advanced circuit classes and understand how to size these circuits yourself, or what we are doing in this work, we actually train the neural network to be able to do that. So what the algorithm shows on the left is it uses kind of evolutionary algorithms to generate some initial search of the space. But then with these samples, it actually goes and trains the neural network through simulation for the network to become just a reasonable designer, in a sense that out of many, many samples that we generate, the discriminator network is just able to basically say, oh, these designs are worth looking further into or not, right? And because now these other designs that are worth looking into, we can simulate them in much more detail using tools like SPICE, we can actually figure out their real performance. And through that, you're exploring the whole design space much, much faster. What we're showing you here is kind of the convergence. The green line is the convergence of this algorithm with respect to the previous ones, because the network can do evaluations much faster than actual post-layout simulation. And we've designed, what I'm showing you here is the layout of actually a full optical receiver, a lot of different circuits in there. And you'll learn if you join this project, essentially to develop a lot richer portfolio of circuits and how these tools work and optimize. Another one, so that's kind of a more analog mixed signal side as well as machine learning techniques. And we have another project that is looking at accelerating machine learning algorithms for inference at the edge. And I think it's kind of a similar project to one of the ones that was already discussed in Professor Koitzer's group. On the left is kind of a typical pipeline for autonomous driving, kind of level 3, where you have locationing, the feature extractor, and then a tracker. All these three algorithms are basically currently run with neural networks. And that's a very simplistic single camera type scenario. You start increasing the resolution of the camera, multiple sensors like LiDAR, start adding actuation in. It becomes an unbearable environment for current GPUs to run in. You essentially start burning a lot of power, adding a lot of compute resources. We're working essentially on hardware that can do that in a much, much simpler footprint. And what I'm showing you on the right is essentially a chip that we designed recently with the RISC-V processor, with a full-blown infrastructure to add an accelerator core. So we call this like a space core. But you have to design this space core in a very hardware efficient way, because you need to pack huge networks, like, for example, in this case, we designed it for AlexNet, into this small chip area. So you have to prune the coefficients, do efficient management, work with the training tool to, at the training time, adapt the network to be very friendly to the hardware architecture that you are implementing here. So if you're interested in digital design and machine learning, this will be a project for you. Okay, I'll also cover the Alberto's project, because I know he's not here. In this project proposed by Professor Vincentelli, they're looking at essentially creating advanced algorithms for energy storage and dispatch. And as you know, the problem that's happening in energy distribution is that all of a sudden you have multiple different heterogeneous sources of energy, like solar, wind, etc. And the distributors are also varied, right? So you need to have an algorithm that will be able to manage all these heterogeneous producers, as well as consumers, as well as homes that have local storage units, and how do you control, harvest information, and then control this whole network. So Professor Vincentelli has essentially a project where students are looking at how to harvest the information from the available resources, and then basically write the algorithms that will propose different management techniques for the distribution and dispatching the energy on demand from local resources as well as global, like area network distributions. And again, collecting the metrics to be able to inform the decision systems on how to do this. There's more details here, and I'll stop. We don't have Anant. Okay, so I'll just then go through his piece as well, and then hopefully Brian will be here. In Anant's project, what we have is, again, machine learning, but for wireless communications. And what's happening here is that if you look at current wireless protocols, you essentially have a whole slew of different protocols by which you different communication devices are trying to interact with one another. It's usually a predetermined protocol. I can only talk to someone if they have an LTE, for example, are on the LTE network. If they're on CDMA network, they won't be able to basically communicate with my LTE system, and vice versa. Multiple people, even on the same protocol, will essentially fight with each other, and that's called wireless interference, rather than being able to collaborate to effectively use the spectrum, right? These multi-user and collaboration techniques are just starting, because if you look at wireless networks today, they're primarily interference limited. There is really, people have exhausted all signal processing techniques and coding to reach essentially a single user capacity limit. And what's really now creating a problem is this interference between sets. So what Anant's project is looking at is how can we use machine learning to do dynamic collaboration and understanding of signatures. Even if I know nothing about your protocol, can I somehow understand how to work with that protocol so that both of us have the lowest possible interference to one another, and in fact, in some scenarios, help each other boost our data rates, right? So that's kind of the project. But underneath the machine learning, you have there's a whole infrastructure of adding the FPGAs and emulating on real radios and learning from actual real experimental test beds, because the devil's in details in these non-idealities of hardware and actual wireless transmission that you get the real data sets that machine learning algorithm can operate on. Yeah, and these are some of the results that they've had. Okay, I think the last one, and I'm just gonna represent it a little bit for Brian. Brian has, over the last couple of years, have very active projects in the VCCG area, and this is on the topic of vision correcting displays. And the idea is kind of very interesting, is that if you could somehow capture the visual aberration of a human eye, let's say if the eye is aging, you should be able to pre-distort the image that's being, let's say, on your tablet, to, combined with that aberration, give the user an actual correct image, right? So now, how do you go about, first of all, capturing these aberrations, and then doing the inverse on a 2D surface to basically capture these 3D aberrations that are happening in the eye? That's actually a challenge in this project, and he has had several students work on it over the last few years in the MNG teams, and they've made quite a bit of progress on this. So I highly recommend this project as well. Think we've exhausted all our capstone pitches. If you have faculty and students who pitch this are still around, I would open really quickly just for if you have any logistical questions for me, and then just let people mix and talk more informally. Any questions about the first part, the program, or any of the capstones that I can answer? Yes. Okay, the question is, can you choose the project that is not under your concentration? We encourage, or we try to place you in the project that has at least your concentration listed as at least one of the areas, right? You saw there are many projects that are, if you look at the list, and actually let me see if I may have, okay, this hasn't updated. Let me go. There is one more project, but I updated it, but it's not showing. I'll just describe it real quick. If you look at the list, okay, yeah, the list has a bunch of projects that have many areas listed, right? So that would be the project that I would advise you to look at to see if your area is in that, right? Through that, you will be able to learn quite a bit. Let's say if you're interested in machine learning and the project lists all these areas and you're not in the DSS, for example, even if you're in VCCG, you'll still be able to take a lot of machine learning classes because they're needed in those projects. And then in the context of the project, you'll be able to learn those techniques even more, right? One that is, when we updated deck, I updated, but I didn't show it. We also have capstone projects that are led by industry. And one of the projects that will be listed in the deck is from Volvo. They are essentially looking to create a driving data set based on kind of the databases that they are using to help with automated driving. So there's a lot of image processing, creating these driving databases, labeling, et cetera, that's happening. And if you're interested in kind of interacting with folks from industry really early on, there will be a faculty mentor on campus who is going to manage that project as well. But if you want to have kind of a closer contact with what's actually going on in these applications, that will be one of the projects to check out. Any other questions? Yes?
In the beginning, you talked about how there's two types of capstones where you kind of split the units differently. Does the project have one of those types associated with it, or do you choose on top of the project?
Yeah, so right now, the question was about the capstone design experiences versus regular capstone projects. Capstone design experiences are kind of also like a pilot set of things that we're trying out. And currently, Alan's AR/VR is the only capstone design experience that we have explicitly listed here, right? We used to have another flavor, which was in the circuits area. We don't have it this year, but Alan's project kind of persists from year to year. It's very successful. So in VCCG area, that will be a highly recommended project as well. Yes?
Besides Volvo, are there any other EECS projects that we can do with industry?
So, okay, the question is, besides Volvo project, are there any other industry connected projects? Volvo project is, it belongs to the class of industry-led projects, which means there will be a capstone advisor primarily is an industry liaison, in the Volvo case, Dr. Sohini. And faculty on campus will essentially also be a liaison, but like less involved, right? Just making sure everything's going smoothly and providing kind of a light interface. Many of the projects that we discussed, like for example, Alan also was showing on his, even though they're held on campus, are very connected to industry members. In fact, if you look at this list of projects, I would say 2/3 of these projects belong to centers at Berkeley. Here's Brian, okay. We may give you a chance. Belong to centers at Berkeley, like Berkeley Deep Drive, Berkeley Wireless Research Center, ADEPT, RISE Lab. These labs are all industry consortia. So you have 10 to 15 member companies, or maybe sometimes 20. And so MN students who come and take one of these projects will have exposure to industry members of those centers. We have typically reviews twice a year. and there's a lot of input basically into these projects already from these member companies. Does that make sense? So some are, typically everything we do here at Berkeley is really very well founded on real input with, about real problems. And that comes from these member companies and gives you also a chance to present that work and interact if you're part of the groups that are there. Okay, make sense? Good. Any other questions? Okay, if not, Brian, I just presented your thing, but if you want to say a few more words, if you want to say a few more words, yeah. Since you're here, I don't want to. I kind of butchered a little bit your, but I wanted to present something at least.
Okay, no, I did tell him I was coming because I had a class actually till 2.
Yeah, no problem, no worries.
Wow, there's very few people here.
Oops. Okay, there you go.
All right. Okay, so yeah, sorry, I actually had a class and I knew I couldn't get here till now. So basically, we've been looking at the idea of can we have a display correct for your vision on each individual basis? If we know what your vision problem is, can we modify the output, the image or the text that's on the screen to compensate for your vision? And it's interesting in one sense, in a purely mathematical sense, it's almost impossible to really do it, but being able to incorporate some elementary optics at the same time as the computational or digital or algorithmic part allows us to actually completely do it. So the idea is you see in the picture, somebody's looking at a display without any visual aid, no eyeglasses or contact lenses. The display is aware of this patient's or this viewer's visual problems, and the output is modified in such a way as to be able to be seen in clear, sharp focus by the viewer. It's primarily computational, so it has the advantage that you don't have to make a physically different device for different people, because the same device will work for everyone else, simply using the parameters of the visual defects of that particular person. One aspect that's particularly important to me, and if you may learn something you don't know today, eyeglasses are a phenomenal device, non-invasive. Your eyes change, you can get new ones without having to get more surgery, really remarkable. However, they also are very limited, I guess I should say. Limited in the sense that they only correct certain visual problems, certain optical problems. The good news is most people are well served by them, but there are certain optical problems that people have that are not corrected by eyeglasses. And there are even some optical problems that those of you who think you're corrected by eyeglasses may not be fully corrected, because the inherent process of eye measurement today, which you go to the eye doctor and they say, what's better, 1 or 2, what's 1 or 2? They're still basically just using lenses, and that does not allow for correction of these more complex optical problems. And those limitations don't apply to what we're doing, because what we're doing is a computational approach. So this means that for people who have these kinds of problems, we should be able to provide them with a display that they would be able to see, even though today there are no eyeglasses that they can do with that. So another thing I should mention about this project, it's rather broad. It brings together a wide set of intellectual activities, ranging from some mathematics, some computer science, of course, some algorithms, algorithm analysis, a little bit of optics, some knowledge of the human vision system, a little bit of display technology, a lot of elements involved here. And I think that that's actually a good thing. It may sound bad at first. I think students may be intimidated because they'll hear the 2 or 3 things that they're not experts in and think that they shouldn't do this. But it's really quite the contrary, because of its breadth, we're able to customize or accommodate the particular part of the project that a student works on, and they can work on what they're particularly interested in. So it's been something we've been developing for a few years, and there's still a lot of interesting problems, both theoretical and practical. I am passionate about it because it does bring together a lot of different intellectual elements, and it's also something that can really help people. And I guess from my own perspective these days, I have some concerns about the social responsibility of what we're doing, and you can be using vision to be doing surveillance and a lot of nasty things. This is something which, as far as I can tell, is only helpful to people. So I find that very inspiring. And okay, so I don't know what Vlad said. I hope that kind of fleshes it out, and hope to talk more about it later.
was just in the interest of presenting something. But yeah, feel free to add on.
Sure. So what we're doing at a very high level is we want to bring machine learning ideas into wireless communication. So why this is interesting? This is interesting both from the perspective of wireless communication, which is a very important area, and bringing these modern tools to bear on that area to see what things you might really revolutionize. Second, it's interesting from a machine learning perspective because it provides a different kind of problem that exercises different modes of machine learning and helps you understand what's going on better. So the big idea that we want to be able to do is to say, can we have systems learn to communicate with each other and optimize themselves as they go, as opposed to having to be pre-specified with a design that says this is exactly how we will coordinate. Being able to do this would be kind of a major transformation for the industry and also allow all kinds of new products to be built. So in terms of the backgrounds that we can use from students that will be useful and that you can bring to bear and feel like, okay, I can be productive. Of course, machine learning is going to be one of those, but there's many different levels of using this. Wireless communication, but also things like digital design, as well as things like networking and signal processing. And the reason the digital design is going to be an important role, can play an important role, is that we want to see if this can actually be made to work with a real radio. And so we have software-defined radios, and they have FPGAs in them, and we might want to use the FPGA to actually do this stuff at something approaching real time. So that's the kind of stuff that this project involves. The big picture is, can we talk to space aliens interactively, right? So we have no idea what they're saying. They have no idea what we're saying. Can we learn to talk? And so we have some initial results that say, we can talk to space aliens. Oh, this didn't even come out. Oh, well. So this is supposed to be like an animation, but like a GIF, but the GIF is not working. So this is actually can help show what's going to happen. What happens? What happens is that we actually have two of these alien systems that don't know how to communicate, that haven't been pre-specified with a way of communicating. We tell them, hey, start talking to each other over the air, and they wander around, and eventually they figure out from nothing a signal constellation to communicate with each other. So we want to see, can we have this kind of purely learned by babbling and interaction thing happen, and how can we exploit it to make engineering systems? So that's the idea.
Okay, any other questions just in general about the program before we break out? There's a number of faculty now here you can mingle with. No, everyone's good, understand. If you have any questions that you think of, and for people who are not here, please feel free to email faculty about capstones, and then Michael and me about just general program logistics. Thank you.